Hi, and welcome back. So finishing up propulsion portion of chapter 3, and then we'll move on to more fun things in chapter 4. But last few is kind of high-level conceptual, but just imagine if we had a streamline, and this is basically just a burner disk, right? So within these streamlines, in fact, we'll make it red for fire, that you combusted something in that streamline, and these are streamlines. And if you go look at all of that and you do kind of the thermodynamic diagram of this, TS, yes, you'd have like a little bit of a pressurized, different kind of things, but basically nothing's going to happen. This is going to cross to 0.2, and then the jet's going to be 0.3, and no work, no work is going to happen. Basically, all you did was create hot air. Right? So if you just had a burner disk that you just added heat to, nothing's going to happen. Okay, so this would be a non-ducted burner. Okay, so we know that's not that exciting from point of view, but if we do sort of two interesting variants of this. The first one is realizing this is really for Mach less than 0.1. That if we actually repeated this for Mach greater than 1, sorry, that was entropy, TS, then you would indeed get a little bit of a pressurized, because first you would actually get your sort of shock, which would increase entropy and pressure and temperature, and then you would have your heat addition coming into this system, such that yes, indeed, you would for sure get some heat addition. So if you could just magically have boom, the kind of supersonic burner. Now, a part of it is actually, and Kuchemann kind of walks in like, well, in that condition, you're actually you're effectively pushing against the shock waves. So it's a thing that you're pushing against, and so you finally have the ability to have this do work on the system. Right? And the other version of this is just a propeller. So again, it's a free stream, and then instead of a burner disk, it's now sort of this mechanical disk where work is being added, not heat. And in this condition, you'd have you actually would have thrust. That's why propellers work. But remember that the velocity here, of course, is going to be far greater, and so we know that the jet efficiency is going to be less than 1. Which, you have to have less than 1 anyways to have thrust. But that's it's sort of a mechanical equivalent to this. But then something interesting happens when you, instead of just having a propeller, if you actually shroud it. And so then you have sort of the shrouded system. So again, back here, we've got some sort of mechanical thing that's adding or potentially even heat. And so in this condition, I'll switch colors to blue. Hopefully the blue shows up fairly well. You actually have your streamlines are going to kind of want to go around this. And so a couple interesting things are happening here. And then again, just treating this as inviscid, if you add in the Kutta condition, right? Then you're going to have kind of vortex shedding, and you have suction that's happening on this side. And so you actually get a little pressure draw, and then you would have thrust. And so in this condition, whether you're just adding heat or you could actually get some propulsion out of it. So if even this is the burner disk, that would work a little bit. Now, interesting things though, because there's suction happening here, a couple things you have to worry about. You actually now have to worry about the Mach number. And so think of a subsonic aircraft that's flying at fairly high Mach numbers, say Mach 0.8 or something. There's a limit on how much suction they can actually do. So there are some size constraints, and Kuchemann walks through some of that, where you would need to keep that below, kind of locally below Mach 1. Okay? And then there's also some off design considerations that you had to think through in terms of, is the flow angle changing, turbulence, angle of attack, things like that. And so, just highlighting that, saying that there's not just as simple as this, and you can get into the curvatures and different estimates of it. And then I'll just kind of highlight from a turbine point of view, there's also an asymmetry problem. So many researchers have actually talked about, hey, the best place to put an engine is actually on top of an aircraft. One, from the sound point of view, the sound would radiate up, not necessarily down because the aircraft is below it. And the second thing is the boundary layer that's growing over the aircraft, you could just have it be effectively ingested by the engine, and you would reduce drag, right, if you're adding work to it. But the problem is, these jet engines are pretty finicky, right? Compressor blades are pretty finicky from an asymmetry point of view. And so that idea has not yet really taken flight because of that asymmetry. It's sort of hard to predict, okay? And hard to have a jet engine effectively handle some of those off-design features. That's one of the things that we're doing here at Venus because of the rocket-based combined cycle. We don't have a compressor blade back there that is going to have issues with any of these asymmetries. It's pretty nice. Pretty nice. And then the last one is Kuchemann does talk about supersonic. And so if you have an air inlet, and I'll draw it kind of both sides here. We've done some pictures like this in the past where that's a nozzle that if the flow is supersonic, you end up generating shock, kind of on both sides, shock. I've drawn here as a compression ramp where it's sort of slowly doing this, and so you would have multiple shocks. And so, if this is M0, here you have M1, you would shock it down to subsonic if you're a ramjet, or you would leave it supersonic if you're a scramjet. And so, this doesn't have to be axisymmetric. It could be, you could have a 2D nozzle, things like that. But just kind of finishing out what supersonic looks like. So just because remember in chapter 3, he didn't actually talk about this. He just said, hey, magically you have shocks. And the one thing we have done so far in chapter 3 is when we're looking at the temperature ratio, when we're looking at the thermal efficiency, and for a ramjet, we really knew that this was just kind of the ratios of the temperatures here, and we ended up knowing how to relate those: 1 plus gamma minus 1 over 2, Mach 1 squared, and then 1 plus gamma minus 1 over 2, Mach 0 squared. So we knew how to relate to get the temperatures, realizing that this was isentropic compression, and going through shocks, it is not isentropic. You do actually pick up some entropy, and so really when you go back to, say, the propulsion efficiency that we were estimating as the jet efficiency and then the thermal efficiency, just realize that at least the way we would talk about it, there's another efficiency there on top of that. You can think of that as just kind of your non-ideal, and just realizing that shocks themselves would be part of that, and that's why looking at the total pressure, your total pressure recovery is one of the measures of how well is your inlet design, and there are mill standards on what the mill standards are there to kind of talk about the total pressure and what's an okay total pressure loss, and just be careful. Those curves are somewhat experimental in terms of they're kind of matching experiment, but they're also intended just to be a curve to just help calculations go quickly. So it's not these days computers are fast enough really that it doesn't take a lot of effort to calculate. Say if you're going to have a ramp or however many different shocks you're going to have, it doesn't take much calculations nowadays to actually calculate that total pressure. And so just be careful when you're using sort of these total pressure curves that you might have done in the 80s because it was way easier to just curve up a quadratic, versus now anybody on Python should be able to run that quickly and get an answer. So the kind of tail end here of chapter 3 was way less heavy on the math, but just kind of starting to talk through a little bit of how you actually would install these systems. Chapter 3 was pretty heavy on just, hey, we're just talking thermo and heat addition and things like that. This is kind of the first taste at, well, actually, what's the thing look like, and is there any considerations? And the answer is yes. Like, you can't just add heat without containing it. You need to contain it here. You can just add work, and that works fairly well as a propeller. In both situations here, you got to watch out for the Mach number on the suction side, because you might go sonic. You of course have to handle any off-design considerations. And then once you're supersonic, realizing that you do create shocks, it is going to create entropy. So this formula is not quite, this would be the isentropic version. It's not quite as accurate. And so just remember to kind of make sure you're penalizing yourself a little bit when you're doing some of the formulas from chapter 3. Okay, and we'll see you next time.